The next presentation is from Work Package 2. Oh, sorry, Work Package 3. Igor Iliev is the next one online. Igor has been working in the Waterpower lab at NTNU, meaning in the lab where I'm sitting, so I have had full control of what's been going on. It's been very interesting and challenging, no doubt about that. So we have done both experimental tests and numerical analysis. Please, Igor.
Thank you. Okay. Thank you very much.
Introduce yourself.
Yes.
I didn't.
Thank you.
Sorry.
For those of you who don't know me or haven't seen me before, my name is Igor Iliev. I work as a research scientist at Sintef Energy in Trondheim, Norway. And I have been working in HydroFlex as a work package leader of the work package number 3. And we have been dealing with we've been doing research, trying to identify how can we increase flexibility of turbines and what can we do to tackle the problem and probably increase the number of starts and stops that the future turbine can handle. So in this work package, which is named the flexibility of turbines, how do we address the main objective of the HydroFlex? So the main objective here is to, as you can see on the left side, is to combine pretty much all research means. That's theoretical analysis, empirical, numerical analysis, laboratory measurements, in order to develop turbine, generator, and converter, as Ole Gunnar mentioned previously, that can handle the future needs of flexibility. And in our work package, we work on the turbine in particular, and we have 4 tasks. The first task is to develop design tools that can help us to do the research and build such turbines. Then the second was to do numerical analysis or to combine the design tool with numerical analysis. The third task was to validate through experiments. And then finally we had another task that is dealing with the lifetime estimation of the turbine. We had 5 partners working in this work package, 3 universities and 2 industrial partners were involved here. So NTNU was the leader of the work package, and we had LTU University, Luleå University from Sweden, the St. Cyril and Methodius University from Skopje, and we had also Rainpower, the turbine producer from Norway, and EDR and Medeso, software company that is dealing with development of numerical tools and software. I was working at NTNU, but I recently moved on to Sintef, so that is why we see Sintef as well here. we had Sintef was also a partner in this project, and for different most activities were focused on different work packages. Now this one as well. So I'll try to summarize what was done in this work package, and as you can see, many people were involved. I list here the contact of these people, and for each slide you'll see the logos in the upper right corner. So if you have more questions, further questions later, feel free to contact any one of these people who may give you more details about what was done. Moving on. On the left side, we have what we call the research cycle of the work package tree. So we came up with a tool that can help us design turbines. Then we use that tool. This tool, by the way, uses numerical simulation software for both hydraulic and structural simulations. And then we use this tool to design reference turbine design, or parts of the turbine, the most important parts. And then we conduct experimental performance check, and finally go back again to the tool to refine it or validate all methods that we have been using. So the idea was to perform at least one cycle of this. And the HydroFlex design tool has sub-parts in it. So we have part that handles the hydraulic and mechanical design. We have part that is performing all the necessary numerical simulations. And all this can be shared to the lifetime estimation tool as well. And everything is returned back to check how our flexibility objectives are met. Let's say that in this work package we define flexibility as increased or untouched or flattened out efficiency throughout the entire operating range as much as possible, of course, and reduced stresses, both static and dynamic stresses. Of course, these objectives can be redefined for different design scenario, and everything is feedback to all the way to the beginning. So that is how the tool works. We have been, in our research, we have been using the Francis 99 model, which is installed at the Waterpower laboratory at NTNU. On this picture, we see the HydroFlex runner and the HydroFlex guideways installed or put in the assembly. The turbine is a low specific speed. It has been used for several research projects previously. It's available in the Waterpower lab, and it's open for anyone to use the data and the geometry. Most of the experiments in our work package are done in this lab, except for the material tests, which I'll mention them a little bit later, which were done in different NTNU and Sintef labs. Yes, so it's a turbine model, turbine rig that can achieve IC standard quality. In the parametric design environment, we have spent some time to define the geometry of the runner parametrically. As you can see, it is defined on these diagrams. We see different combinations of the 15 parameters that were used to define the runner, and they have different values here, so you can see how each parameter is affecting the geometry. On the other side, on the right side, we have the guide vane parameterized We have just 4 randomly generated guide vane designs. You can see that, for instance, the thickness of the guide vane changes, the length of the guide vane changes, and other parameters as well, which were used in the design tool. Of course, I cannot speak more about the details here, but you can find the relevant information in the or all the information you need in the relevant publications. So we used these were, by the way, MATLAB codes, and we used this scripting method to create output files that can go straight into our numerical simulation tool provided by the commercial software ANSYS. So we have, once the files go in the ANSYS software, for instance, here in this tab we create the meshes. In the upper part, we use TurboGrid, and we import curve files to create the hydraulic domain, and then exported is the mesh. Here shown the guide vane and the runner. On the lower part, we have some operations done in SpaceClaim to finish the geometry and identify a sector. And then finally the meshing. As you can see here, the fluid bodies are not shown, but they are also included. So the runner is simulated submerged in water. These meshes then go further on into the simulation part. So we simulate, this is a workbench style presented print screen directly from the workbench project. On the left side, we have the first part is the fluid simulations. These are actually transient simulations. And then we have 2 more, static acoustic and harmonic acoustic simulations. So the first one performs the transient simulation, then the oscillating fluid, that's the important part. The oscillating fluid pressure is loaded onto the structure and previously decomposed using Fourier series decomposition into the frequency domain. And finally, the structural analysis are performed in the frequency domain, harmonic analysis. So what we can see there is actually the mesh that is shown there is not the actual mesh that is used. That's just for demonstrational purposes and initial tests. But we have here the total deformation on the left and the imposed pressure field on the right. For 2 nodal diameters. So this is the transient.
Recording in progress.
Thank you for that. So as I said, using these tools, we had to design reference geometries to conduct our laboratory measurements. The geometry of the HydroFlex runner was, at the time, we didn't have ready the part of the tool that is dealing with automatic optimization from the structural part, was not ready. So we used only the hydraulic optimization part to optimize the geometry. And then later we performed structural checks just to make sure that everything works well when we put it in the lab. So what I show here is just some CFD results. The original turbine that we're using, the Francis 99, has its own runner, but we have designed a replacement geometry because we wanted a geometry, reference geometry that comes directly from our tool so that we can directly verify all the numerical methods. And as you can see, CFD results are quite interesting and pretty capable to capture the trend. We see that the turbine has the highest efficiency at one operating point, and then as it goes back and forth, the efficiency reduces, and we can see, for instance, for that operating point, why is that? That is because the flow field is not well aligned inside the turbine passages, where we have additional losses. And that is the wetted surface of the HydroFlex runner. As I said, we used structural simulations to first to check the structural integrity, and then we used the principal stresses result, the maximum static principal stresses result, and strains to identify two locations on the trailing edge where we would like to do strain gauge measurements. Why is this important? That's important because when we operate the turbine at off-design operating conditions, it will be subjected to transient loads. And at the trailing edge, we can see we have maximum stresses locations. And that's where typically we have cracks on the turbines, which is something that we want to avoid if we want to design flexible turbines. So we want a turbine that will not be damaged and can sustain operation at different operating conditions, of course, in the entire range. So we used numerical simulations to identify locations for strain gauges. You can see them marked there. And this is how we designed the structural or the mechanical assembly of the HydroFlex runner. We try to reuse the hub and shroud that were already available in the lab from previous research. And then what we did is we just redesigned the blade. So this assembly is a modular one, so we can later, if we come up with even better design or different design, we can always test it just by replacing the blade sections. Another important feature was that with this design, we know exactly where the connection is. And that's very important for when we do the structural simulation validation. So with this runner, we have solved some of the drawbacks of the original Francis 99 runner that were identified in previous projects. And finally, we wanted to have the center bushing and the cone. That's part where we will put onboard instrumentation. Because as you can see, this runner is rotating, and we want to perform measurements in the rotating frame of reference while it's rotating. So we need some equipment to be installed in the runner in a watertight place. Electronics, for instance, that should survive the operation of the runner. So as I mentioned, in the central part, this is how, for instance, the amplifiers will be stacked inside. So we use 3D printed parts. We have a PhD student that is working on this to stack the local amplification. And on this diagram, you see, so we plan to do strain gauges and pressure sensors. We plan to install strain gauges and pressure sensors. The signal will be fed into local amplification for improving the signal-to-noise ratio. Then that goes to slip rings, so that's the rotating domain, and in the stationary domain, it is transferred once again through the slip rings, and finally in the data acquisition module. Of course, together with the rest of the turbine performance, which is that part, the turbine test rig. For the strain gauges, because we finally want to know what the stresses are, but we can only sense the strains, which is the elongation of the material, relative movement, we came up with a hybrid calibration setup. So what we have here is we came up with what should I call it? Fixture for the blade with a pivoted arm where we can install weights. You can see the strain gauges, they're connected to the amplifiers. And then we can load the structure, see what voltages we get, And then we replicate the entire setup numerically and find out what the stresses are in those, strains are in those locations. So that is how we intend to perform the calibration. By the way, there is no good way to calibrate strain gauges mounted on complex structures. If it's a simple beam, maybe we can use analytical solution, but with this double curvature blade, it's very complex. So the only option was to rely on numerical simulations, very accurate numerical simulations. We also, as I said, plan to install or have installed pressure sensors at the leading edge, and this is how we plan to calibrate them. The entire runner will be submerged in that tank and pressurized. And then we have, through that shaft, we have all the wires coming out and connected to a PC where we collect the signal, record the signal. For the guide vanes that were designed, the reference geometry of the guide vane, we have the standard torque measurement, and here I give some pictures of that setup, how it is supposed to look. So the blade is fixed in that jig, and then we apply torque. Here I only show, we have only one part, but actually on the other side we need to have another pulley, another weight, so that we apply only pure torque. We have on the top part of the figure, on the left we have the regular guide vanes, which are used in efficiency measurements, but on the right we have a special type of the shaft where we can we have mounted a strain gauge, which is calibrated here and is used to measure the torque during operation, but the torque, the static and the fluctuating torque due to the RSI. You will, those of you who will join us today in the lab tour will have the opportunity to see these devices there demonstrated. We had another research part which was not parameterized at this stage, but it's a research that tried to control the residual swirl at the outlet of the turbine runner. So when the turbine is operating, especially at off-design operating conditions, the flow will have a residual swirl at the outlet of the runner in the draft tube cone. So this research was done in order to try and control that residual flow or reduce it. And by doing so, for instance, in part load, try to even mitigate the pressure pulsations as well. By doing this, of course, the researchers have tried to increase the efficiency and reduce the pressure pulsations, which should translate in increased flexibility of the turbine. The results are very promising. They have done the way those guide vanes are installed in the draft tube cone, they can move. So for several positions, measurements were done in the lab, and the performance was checked, and pressure pulsations as well. So they installed pressure sensors in this draft tube cone, and the pressure pulsations level were recorded. It's of course it has its pros and cons, but with further investigation, I think this concept can be much more improved, of course. We had another, as I mentioned earlier, lifetime tool was developed by our partner Rainpower. For that, they needed a lot of experimental data coming from material specimens. And experimental data, I mean fatigue data for these specimens. So what you see on this diagram is we can see that some of the specimens had defects. So when a turbine is being manufactured, of course, there will be a manufacturing process, and there will be maybe welding. The material may come with some defects and cracks inside. So the idea is that to check how these defects affect the material or the fatigue lifetime. Finally, all the data is collected and gathered in one tool. On top, we see some print screens of that tool, where statistical analysis are further being performed to identify what would be the remaining lifetime of a turbine. Of course, what's important as an input is the stress fluctuations for different operating conditions. So stress fluctuations using, for instance, rainflow counting and other maybe Miner's rule, one can translate from an ascent curve to a partial lifetime of the turbine. This can be coupled, both can use experiments from the numerics, for instance, can use data from the numerics or from experimental for a particular runner. As I said, most of the details are included in some of the publications that we have. Some of this is already published. We have several submitted, but more will come because as we collect more data, then the writing part will kick in. So stay tuned for those of you who are interested in different parts. And yes, I think I'm done here. Thank you very much. And I'll be... If you have questions, please, feel free.
Good morning, everybody. I won't have any questions because we are part of this work package and we gave our contribution in this work. But since this is the last workshop, maybe this is a part of discussion which will be conducted at the end at the panel discussion, but I really wanted to express my pleasure as the university to the coordinator, to Gunnar, and to Igor as the work package leader to be a part of this team. I think we came a long way from the beginning, and the results that we provided here, I think that they also involve the optimization part, the automated approach, but also the part which is part of the bigger whole, including the guidelines and the spiral case and the part that is NTNU is assigned to. So I'm just saying that thank you for both of you for the being able to be a part of this partnership. Thank you.
Thank you very much. It was a pleasure to to lead a very talented group. Yeah.
Igor was your master student and also PhD student. I was also his supervisor doing it, so yes, we are both proud, no doubt about that. Any other questions?
We have one there, one there.
Hi, Igor.
Hello.
If you know what you know today, would you have done anything different from the beginning?
Yes and no, I would answer. Yeah, of course, there are so many research steps that we could have maybe done a little bit better and improve. But in the end, I still believe that what we have achieved today is a very good job. We have done a very good job all together as a work package. So there are obviously some parts that can be improved. Some of the results came as a surprise to us, so of course if we knew that, then we would have done them or prepared the research a little bit differently to reflect this knowledge. But yeah, that is minor changes only, here and there. Not much. Yeah, thank you.
There is a question on the strain gauges. It's quite interesting that you can measure on the model turbine. Do you expect large enough strains that they are measurable? Have you looked into that?
Yeah, that is one thing. Of course, on the model size, yes, the model is very stiff. So we will be able to measure static strain for sure, but the transient strains may be covered by the noise, the typical noise of the signal. So we do have some ideas how to overcome this, of course, test at different operating points. But yes, that was one of the main concerns when we were designing the experiment. What will be the response and how well can we identify fluctuations or strain fluctuations from the noise that is normally built in the signal. Yeah, so.
Hi, Eric from Stackcraft. I thought the draft tube vanes were interesting. How about at best point efficiency? Did they bother the flow at all? Were they invisible? That's the one question. And also, this is very much in the spirit of the Horizon 2020 sister project, AFC for Hydro. I imagine that there, and I don't really know, but were there some good, how should I say, well, did the project help each other? Did you collaborate on tasks, or were there shared results that are interests to both? That was number 2.
So that's 2 questions. Thank you very much. The first one, these movable fins or guideways in the draft tube cone were designed so that have minimum impact in the best efficiency point. And of course, so they were positioned to follow the flow stream in this operating condition. And they were envisioned to change in angle. For now, it's just the first part, but they can perhaps be designed to change the entire, to tilt the entire body of the fin. I don't think we saw significant impact at the best efficiency point from them. I don't remember. And the second question, no, we did not collaborate in these tasks.
LTU is partner in both projects. So yes, they have access to their results from this project as well. Yes.
Yep. I don't remember direct kind of discussions or collaborations at that time, but of course they can communicate both projects and exchange data. Yeah, of course. Everything will be open, by the way. So not only that project, but any other project can start from there and build it or use the data.
I have one question.
Yes.
Can you go to the position of these strain gauges? The location of them are kind of in an area where we, at least at the hub there, you have placed them in an area where you have large gradients of the strain.
Yes.
Do you think that will give you an uncertainty? I guess the position then is not 100%. When you do it manually, you know that the position will be a little bit off, maybe. What's your comment on uncertainty for this?
Yes, they will be manually placed or installed on the blade, and our lab technicians have tried their best to position them where we want them to be positioned. And obviously, when they're placed like that in the gradient of the strain field, small position change will introduce uncertainty. So we tried our best to install them where we want them and later measure where they're exactly installed and then reflect that in the numerical part. Ideally, we would want to install the gauge where the maximum is, but that is where we have a curvature due to the fillets, so, and that area we cannot mount them the way we want in that area. So that is why a compromise has been made to install them in another remote place and then use results to sense what is happening at the maximum. So yeah, some uncertainties, of course, with experimental methods must be accepted. Yeah.
Any other questions?
Have you tried these strain gauges? Have you tested them already, or are they planned to?
Everything is, they're not test, or the model test is not conducted yet.
Okay.
But the calibration and everything, all of that is been done. So the
For how long do you think you will have data, and when will they destroy themselves?
Well, we hope that they will not destroy themselves in our measurements campaign, but I think we will spend maybe 2 or 3 weeks conducting experiments, full days in the lab.
I guess you have experience with them failing.
Maybe you can talk with Michel about Corius.
Yes, the strain gauges are not the most, the strongest part in the test. So yeah, we expect that they may fail during the experiment, but we hope for the best, of course. Thanks.
All right. Thanks, Igor. Thanks a lot.
You're welcome.
Hello. So let's go for a coffee break, half an hour. So let's be back in 11:45.